Okay, so good morning, everybody. Thanks for coming. Today, my colleague Steiner is here, and me. I am Francesc Alted. We want to talk you some things about how to improve your big data application by using techniques that are quite fundamental, but I think they are going to kind of change the panorama of how computations will be made in the future, in my opinion. So what does this mean? Having high performance, increasing the performance of of the big data application. So on one hand, we meant that we want to improve performance. Okay. So compared with other existing applications like NumPy or typically Dask on top of ZAR, we want to get better performance than that. And then on the other hand, we want to use or to compute with compressed data. So we are having a big advantage, especially with other solutions like NumPy that doesn't handle compressed data. Okay? So this is the goal. And that allows you, of course, to save money. So how we are going to achieve this? So what we did is to create an application with several layers, and we fine-tuned very carefully every part of this stack. And on the bottom you will see the storage layer, then on top the multidimensional layer, computational layer, and finally the API layer. So we are going to explain bit a bit the different layers, how they work. But the idea is, essentially the idea is that the storage layer manages the compression, okay? So we are minimizing the amount of data that the computational layer is going to handle. And then, of course, what we need is to fuse as much as possible the computational step with the compression step, so that we reduce the management of data as much as possible in memory buses. So before proceeding further, a few words about who we are. So I am Francesc Alted. I am physicist by training, computer scientist by passion, and I am open source enthusiast by philosophy. Probably most of you will know me because I am the founder and main developer of BLOSK and PyTables, which are open source projects. So.
Hi guys, my name is Christian. In the past I spent a good part of my career in the financial industry building low latency trading systems, and this is basically where I started to get addicted to performance and efficiency, and I noticed that in other areas this can be beneficial as well. So now my focus is, when I moved on, to apply those methodologies that I've learned on a bigger scale, where obviously the timings are a bit different, but still the problems are similar.
Yeah. Okay.
Back to you.
So I will proceed with the lower parts of the layers, because I am more very close to the metal in spirit. So for the storage layer, what we decided to go is for the blocks library. So for those of you that doesn't know what BLOSK is, it is a library that is specially meant for compressing binary data. Okay, it uses the blocking technique as explained in different articles in our website. But the idea is to reduce activity in memory as much as possible, and it can achieve performance because it uses single instruction multiple data instructions in different processors like Intel or ARM or Power. Okay, all of these optimizations has been done for the next generation of BLOSK, which is called BLOSK 2, and it also leverages multi-threading capabilities in order to take advantage of as much scores as possible. So these two things combined makes BLOSK really fast. One nice way to see how BLOSK can accelerate computations is this plot, which is described in this blog post that I encourage you to read it. But the main idea is that when you have to compute In this case, we are computing the accumulation of precipitation in some part of Europe. So this is real data. Okay. So the accumulation in a certain region of Europe. And if we are doing the computation, the accumulation without compression, which is the blue bar, we can see that we have like a maximum when we have with 8 threads. Okay. This is because 8 threads is kind of maximizing the throughput to memory because of the architectural reasons. However, when we are using compression via BLOSC, we can see that compression initially slows down the computation, which makes sense because it needs to be decompressed and compressed again. But when you throw a good number of threads at work, eventually the throughput of using compressed data will win to the throughput of uncompressed data. So the idea is yeah, you have a question? Yeah.
How many cores were on this machine?
This machine, I think they were 28, but with hyperthreading it's 48. Yeah. I think it was no. This was an AMD, so yeah, I think it's 24. So yeah, 24 is, yeah, exactly. So the take-home message is that don't blindly think that just adding compression to your computations is going to slow down your computations, because in some situations this is not going to be true. And in my opinion, the industry is changing a lot, and it's putting more and more cores, and these kind of situations will be more and more common in the future. And they are happening already for some kind of computations. So another nice thing about containers in BLOS 2 is that we provide different containers. So one is called superchunk, and the other is called the frame. So the superchunk is mainly sparse, and it is designed to store data, compressed data in memory. And then the frame is sequential, is stored sequentially, and it is designed to either store data in memory or on disk. So depending on your needs, you may want to use one or the other. Okay? So we have flexibility in that sense. Also, we created a new format for storing the compressed data. Okay? And the new format is essentially the frame. Okay? So when you see the frame, this is sequential, and of course we need a format in order to interpret what's in every part of the frame. So we created a new format because it is critical for us to find a way to store and retrieve data efficiently, right? So, and also it's important to adopt open formats, in our opinion, for reducing the maintenance burden, and also to facilitate the adoption more quickly. And BLOS 2 brings exactly that, an efficient way to open format, an efficient and an open format for persistency. You can read more about the format there. It's a very simple one. It is based on message pack, and it is around 4 or 5 pages, so it's really, really simple, especially when compared with very complex formats like HDF5 or NetCDF4, for example. Another feature of BLOS 2 is that it adds the capability of adding meta layers on top of BLOS 2 containers. Okay, so in the bottom we have the BLOS 2 container, and then we can add different layers for adding information about what you are storing there. Okay, so you can add layers for describing the multidimensionality of the data, or describing the types of the data, or whatever. But then you can, on top of this layer, you can put another layer, or even more layers, for describing more general situations, like, for example, describing a data that is meant for storing data for microscopy, or machine learning, or financial data, for example, whatever. So this is very nice because it allows to create like applications that builds on top of existing layers. So you don't need to add the layers by yourself. One of the layers that you are seeing there, it's called Caterva, and this is what I am going to describe. But this is essentially a layer on top of BLOS 2 that allows you to describe multidimensional data. So what's Caterva? So Caterva is an open source C library, but also a format that allows to store large multidimensional data, chunked and compressed data sets. So data can be stored either in memory or on disk. But the API for handle both versions is the same. And compression is handled transparently for the user by leveraging the BLOS2 library. So the user is not really aware that the data is compressed because he just asks for data, and the data is compressed and decompressed transparently for the user. So the Caterva meta layer is actually very simple when you store it. So it is just a few bytes describing the number of dimensions that you want to store in this container. Then the array for the dimensions of what you are storing. And then another array for the partition dimensions, which is the same concept that chunks in HDF5 or ZAR, for describing the dimensionality for every chunk in the data set. Okay. Of course, this meta layer can be modified so that the shapes can be updated. And that means that we can resize arrays. We can shrink them or we can enlarge them. Yeah. You can find more information about this here. And Caterva is essentially meant, Caterva is not meant to be used like in the cloud. Caterva is more meant to be used as a container for data that is in memory, or maybe data that is stored in very fast solid-state disk. We fine-tune Caterva quite a lot to be very, very efficient in these two layers. And for us, these two layers, memory and solid-state disks, are part of the memory storage hierarchy in modern CPUs. Also, Caterva brings powerful slicing capabilities. So when you have a multidimensional array, you want to access data from this. And we provide machinery, the machinery for retrieving the data. So in this data set, we see that the small cubes are what is called the partitions or chunks. Okay? So when you ask for the chunks that are in yellow, Caterva is going to figure out where are these chunks located, and they will, Caterva will extract them, will decompress them, and will hand out the data for you. Okay? So, as I am saying, Caterva is about multidimensionality, also about chunking. And most of you that are familiar with handling chunk data, you must know how critical is choosing the chunk size of the different sizes for the different shapes of the partitions. Okay? So for those of you that are not familiar with chunking, let me put an example of how critical chunking could be. So let's suppose that we have a small a data set that is stored. This is a two-dimensional matrix, and the chunks are the lines in yellow. And we want to access. Let's suppose that we want to access to this row. Okay. So what's going to do Caterva or other chunk storage is to retrieve this chunk, and that's all. The other chunks remain untouched. So this is very efficient in this case, okay? But what happens when we want to access the data in the column axis instead of the row axis? We need to touch every chunk, right? And as a consequence, we need to read the whole matrix, even if we want only one single block, one single column, okay? So maybe if we want to provide like better access in x-axis and y-axis, maybe a better partitioning would be to create these squares. Okay, so make the chunks as squared as possible, so that if we want to access these values again, we only have to decompress only 3 chunks, not the rest of them. And if we want to access the column, we only need to decompress, again, only 3 chunks. Make sense? So, of course, when we are going to deal with compressed data, we need to use chunk data because we don't want to decompress everything in order to access one single element. But on the other hand, this chunking capability is also providing us a way to fine-tune the pattern access for our datasets. Okay, so a brief comparison against well-known chunk containers like HDF5 or ZAR. So Caterva supports most of the things, except that Caterva is not hierarchical. So typically, you store one data set per container. If you want a hierarchy, you may want to use a file system, for example. It is not yet mature. I mean, we are developing it. Probably, I mean, the format is completely established, but we still need to make it available in production. It's already in beta. And one of the distinctive features is that for the memory version, we support both the sequential format and also the sparse format. So depending on your application, you may want to use one or the other. Okay? So in the demos part, we are going to show you why this is useful when you are accessing data. Okay, so I will hand out now to Christian about the computational layer.
Exactly. So yeah, I will talk a bit about the computational layer, because it's great if we can basically extract data and store data very efficiently in memory. But I think most of us, what we really want to do is actually compute something. And as you already can see here from this layer, we're going to make heavy use of existing technology in order to be efficient. And when we talk about computations, in this case, what we mean is mostly expressions, because, like, let's say a single operation is usually not that common, and more common is that you have like a series or a chain of different operations that you want to apply to your data. And so that's why we focus on the expressions. And so Francesc already introduced this concept of chunks, and this is going to be crucial here as well, because when we evaluate the expressions, what happens is actually that we're going to operate on a chunk by chunk basis, and we will make sure that those chunks are small and fit in the CPU caches. So that we can optimize it properly. We're going to do this basically by compiling the expressions with the help of LLVM, which is quite a well-known compiler toolkit that is also used in the Python community, for example, for NumPy, maybe other applications that I'm not aware of. And what it's useful for is basically to make sure that when we have large expressions, that we can avoid temporaries, that we can fuse the loops of the operations itself. And one very nice feature as well is that a user basically can write like a custom operator in Python that then will be compiled to LLVM IR, and in the end machine code that then can be applied together with the expression. Also, we will make use of the well-known Intel libraries for math functions that are also used by, if you install the Conda editions, by NumPy and SciPy. And so that was basically the summary. So if we get back to the benchmarks that Francesc has shown in the beginning. It's always good to show a bit the environment where those benchmarks have been created and the test data that we have used. So the benchmark have been executed on Azure on a compute optimized VM with 4 CPU cores, 8 virtual CPUs. And the test data set is what Francesc already said, is precipitation time series data from Central Europe. And the whole data set is 22 gigabyte on disk, which gives you this grid as indicated below. And if you go to the first benchmark, which is basically extracting data, you can see that our efforts are still work in progress, because here in this use case, for example, the SAR and tasks is slightly more efficient than using our technology, but it's a very small, let's say, difference, and it will be amortized by the gains that you have from the computational layer. but I think it's fair to say that it's still work in progress. And so what's being done here is we create like a smaller data set from this bigger 22 gigabyte data set that is on disk that we're going to use in order to do the computations. But as you can see, for example, HDF5 and Task is pretty inefficient if you compare it with SAR and Task or with our solution. So when we come to the computations again, so the what you can see here as an example is this expression with involving transcendental functions and constants. And what we can see here is that here our solution would really shine, even if you compare it to NumPy, which operates entirely in memory. So as you can see, I mean, it uses a factor more memory, obviously, because it's not compressed, and yet it is slower. So this is due to the effects that, or a lot of different effects, but that Francesca and myself have tried to explain. You have a question now, or you wanna?
Is this using multiple CPUs or one?
This is using multiple. This is using all the 4 CPU cores that I have. So here.
For NumPy as well?
Yes, yeah. I mean, yeah, it's a tricky question, I would say, right?
No, I mean, NumPy is using NKL behind the scenes in order to evaluate the sine and the cosine. And NKL can use also multiple processors, right?
Mm-hmm. Yeah. Okay. So maybe if you want to discuss more of that, we can do that in the questions and answer section. So now completing this stack, so what we need, because we were only talking about C code so far, basically, right? I mean, all these layers are based on a C kernel, and what we really want to have is an API for the end users, and we also have that, especially for this conference important Python, which is what Francesc is going to show you in a second. So just to recap quickly, so our stack, the whole thing is called IronArray, which is a C libraries with wrappers for Python and Java, which can perform complex computations on compressed containers. And Francesc already introduced Caterva, which is this middle layer that provides the multidimensional container. With that, I hand over back to Francesc for the demo.
Yeah, so I was going to show you some demonstrations, both about Caterva, which is the library for the multidimensionality. We created for that a binder, service. So you just can click here, and you can do it yourself if you want. So it takes a while to create that, but you just need to go to the Caterva repository, especially in the Cat4Py. Cat4Py is the wrapper, the Python wrapper for Caterva. As I told you, Caterva is made in pure C, and Cat4Py is a thin layer on top of Caterva. Okay, so this has been loaded already. So let's start just to have an idea how the API works. So first of all, we need to import Cat4Py and also NumPy, typically, because Cat4Py, of course, is optimized for interacting with NumPy. So in order to create what we call a NumPy array, we are going to create an actual NumPy array, and then in order to get an NP array, which is an object from Cat4Py, we have different ways to do it. The first one is just use from NumPy. Let me increase the font a bit. It's better to read? Okay. So this is the first way to do it. It's very fast. Then another way is to create a container and then start to fill it like chunk by chunk. Okay. So for that we implement small an iterator that is meant exactly for creating compressed data containers. And then with that, we can fill chunks of this A, which is a NumPy array, and we can fill the different chunks for the destination. Okay? So this is going to be useful when, for example, you are creating data sets that are bigger than memory, and you cannot afford to create the NumPy array first. And finally, we can create also, just for a generic buffer, okay, we can create the container, specifying the shape, of course, and specifying the D-type, data type that we are going to use. These are the different ways to create an NP array. And also an interesting thing is that during this process, we haven't specified the partition size. So what happened with the partition size or the chunk size? So we put some kind of intelligent algorithm in order to compute like a reasonable chunk size for people to use. Okay? So in this case, we are asking which is the partition size that has been computed, and the partition size is 26 by 5,000. So typically what this algorithm does is to favor the way how the layout is stored in NumPy, because most of the people want to optimize the layout for NumPy data access patterns, but they are allowed also to add, for example, a p-shape here, another parameter, and specify, of course, the partition size that they want. Now, we also provide a read iterator for the arrays. So in this case, it is called iterRead. So essentially, it is returning the block, which is the NumPy array for the partition or for the block, and then an info part that is just a named tuple that is providing some meta information about the position of the chunk that is going to be returned. So if we run that, we can see that everything has done a very good round trip, because we are comparing the different slices in the NumPy array with the blocks that are being returned by this iterator, which is stored in the B3, which is the Caterva NP array. Okay, make sense? So of course, we can also get a slice, which is the essential part of Caterva, getting slices very efficiently. And we ask for some slice. We are going to get a NumPy array, which is the expected thing for Python users. And finally, I'm going to show how to serialize a Caterva NP array. So the typical way to do it is to build a new container here, for example. And then once we have this container, we can use this 2S frame, which is the name for creating a serial frame. A frame that can be sent to another machines. It's kind of a bytes, or stored on disk, or whatever. Okay? So this is very simple to do. However, by default, when we create NP array, I told you that BLOS supports two kinds of containers. Okay, the sparse container and the serialized container, which is called the frame. Of course, converting from by default, this is going to create a sparse container because it's more efficient for in-memory containers. But we can also specify that we want to store, to create the C2, this is going to be stored in a sequential frame, not in a sparse frame, but in a sequential one. So what's the advantage of creating on a sequential one? So the main advantage is that when we create the serial frame for an existing frame in memory, this is going to be like memory, no memory copies involved. So let's see how it goes. So we see that the time for creating a serialized array is much smaller here than here, because here a conversion is being done and here no conversion, no copies are done at all, which is very, very interesting.
Probably move to the other example.
Yeah. And finally, you can also persist data very, very easily, also just passing the file name here, and you are persisting. When you are creating the frames or the containers, you can specify the data. Sorry? Yeah.
When you start doing the persistence, do you include as part of the standard some sort of checksumming or way to?
Not yet, but it is planned. Yes. The idea is to create a fingerprint at the end of the container, so that you can make sure that all the data is safely stored, and you can check that the data doesn't have any issues. Okay. Yeah. With that, let's move with an IronArray example. So for IronArray, can you read this? Yeah. Okay. So here we are importing IronArray. And then we are specifying different parameters for, we are using compression, right? So this is specifying the kind of codecs that BLOSK is going to use. So BLOSK can use different codecs. In this case, we are going to use LZ4, which is one of the fastest codecs available. And then compression level 5. The number of threads can be specified as well. And also we are going to specify the number of slices that we are going to retrieve for a big data set. And we are storing all the compression parameters in a dictionary here. So these are going to be the expressions that we are going to compute, like this with transcendental functions, like sine and cosine, and this just arithmetical expression with several operands. And then our data set is the 22 gigabytes that we were referring to. And it is stored in this directory here, okay? And it is in format IronArray. Essentially, it is BLOSK with a meta layer of IronArray. This is what it is: meta layer of Caterva and then a meta layer of IronArray. So if you look at that, you can see that the data is not read in memory; it's just opened from the disk, and the data can be used to extract from the disk, okay? This is also a nice feature of IronArray and Caterva as well. So now we are going to get different slices from this very large data set, 22 gigabytes. I'm not going to enter into the detail, but typically I am going to use the same write iterator than in Caterva, but the one specific for IronArray, which is going to create the new operands, block by block. Then we are using different random positions in order to extract the different slices on disk. So from now on, we are creating the new containers in memory, okay? Because here we are specifying with this that we are creating the new containers. The slices are going to be in memory. Because in the end, IronArray is more meant to do operations within memory data. We are interested in operating with compressed data in memory. So this is the first slice, second slice, a third slice, which are going to be used as operands for the expressions. We have different compression ratios, of course, because depending on the slice that you are extracting, you get different compression ratios because data is not uniform. And then let's go with the computational part, where we can see that we are doing the evaluation by instantiating this exp class with some compression parameters, which are going to be the ones that are used to create the final result here, and here the different flags for the evaluation. In this case, we have different ways to do the evaluation. We're going to use the most efficient one here. Then we bind the different parameters to different variables in the expression. We compile the expression. So this expression, it's if you remember, is this one, the sine. Okay. And then let's do the operation. So in that case, it took around 2 seconds to perform in IronArray. So everything is compressed. Okay, in this case, even the output has been compressed as well. And here is the comparison with NumPy, which is doing exactly the same thing. It's just creating another container for NumPy, and we are going to pass this container here. But we are evaluating exactly the same expression. So let's see how it goes for comparison. So it is 5 seconds. Okay, so it takes like twice as much as IronArray. Okay, so this is a first demonstration of how efficient can be using compression and also multi-threading with IronArray. And then just for the matter of comparisons, we can execute the second expression here, which is this one. It's going to take 4 seconds in this case for IronArray. And then for NumPy, it's taking a while. I don't know why. So 8 seconds. Yeah, again, we have like a factor of 2 of improvement, which is the thing that we are going after. Trying to demonstrate that IronArray can do efficient performance, efficient computational computations with compressed data. Okay, so that's mostly all. We still have, so thank you. We still have, well, you can get much more information in these URLs. And yeah, if you want to ask anything, we are here for trying to solve that, okay? So any question? Yeah?
In the comparisons with ZAR and Dask and HT5 and Dask, were you using the same compression?
We are using exactly the same compressions, yes. So you know that ZAR is using blocks behind the scenes, so we are using exactly the same setting, of course. If not, it wouldn't be fair, yeah. Mm-hmm. More questions? Yeah?
In the iter read block and iter write block, what was the difference between the things returned from those two iterations?
The things that?
What was
the change?
Yeah, what is the difference between iter read and iter write?
So iter write is for creating containers, and iter read is just for iterating on existing containers and getting chunks of the existing containers. One is meant for creating containers, and the other is meant for accessing containers. Mm-hmm. Yeah. Yeah.
There's trade-offs, but one, have you considered having a default partition size, I guess what you called it, that matches the SSD read size?
Yeah. Yeah, as I told before, we are more meant like to be efficient in memory compressed data. But of course, we can also think on providing some functions for providing efficient block size or chunk size for memory that data is on disk instead of memory. But no, I mean, by default, what we are doing is to create a chunk which fits comfortably in L3 cache, so that the operations doesn't have to, I mean, the intermediate data of the operations doesn't need to travel into memory, but can stay in the cache of the CPUs for better performance. That's the thing. Yeah?
So in the hierarchy picture that you have there with the storage layer, and you kind of represented BLOSC in the storage layer, I was trying to get my head around, because I'm relatively new to ZAR, BLOSC, name it. When we start thinking about how to actually persist the stuff into various media, whether it be file systems or storage in the cloud or whatever, is there another layer that we're kind of not describing here, which is what BLOSC would eventually persist to? Or is it kind of assumed that you have like a local drive or local disk, whether it be an SSD or whatever?
No, I mean,
are you optimizing
yeah,
more
at
for
the
like
moment,
local-
it is like this. So it's using the operating system's file interfaces, right? So
Okay.
it is not optimized for anything like in writing to S3 or whatever. So it's
Right.
really just
So it's kind of optimized, I think, more on sequential I/O is better kind of local file system
Yes.
as opposed to a distributed backing system.
yeah, it depends, right? So let's say in the older world where you have a distributed file system but abstracted away by other, let's say, by a distributed file system itself, right? There it doesn't matter, it's opaque, right? It's only if you would wanted to implement it yourself by using S3, then this is not really, I mean, then you can do it by yourself, but it's not supported in that
It's not
sense.
our goal,
It's
so
not
to
our
say.
goal.
Not one of your goals.
Yeah,
at the
exactly.
moment then.
yeah.
Because our belief is usually then you have to look at the overall problem, right? Like because if you just provide such a facility out of the box, then it might try to solve part of a problem that should have been solved differently in the first place. At least
So, I
that's
mean,
my opinion. But
So looking at BLASK being used by ZAR, and obviously ZAR does have all of these back-end, broader distributed storage engines. How would you kind of describe the philosophy? And I mean, this is a whole stack, right? Where you've got BLASK, Caterva,
Yep.
IronArray. The other one's more like ZAR using BLASK that might go to distributed stuff. And so rephrasing kind of like what you were saying here, this stack is designed more for like a local, sequential, using the OS, that kind of stuff. So
Exactly.
Okay.
Yeah, that's the thing.
I mean, we also intending to kind of come up with a model for a larger distributed case, but we're not there yet. Yeah, that's true.
And also, when you are trying to get the most of performance out of that, you need to be very careful of how to merge the compressed data with the computational layer.
Yeah.
So, I mean, we need to be careful that we are not getting data from the cloud, because this is going to kill performance, right? So typically, this is why we are interested more in the layers that are very close to the CPU.
It's hard to tell whether doing it from the cloud is going to kill performance if you have really massive concurrency in big pipe.
Exactly. That's why I said it's part of the overall problem then that has to be looked at, right?
Right,
So
it's a weird world because we got NVMe SSDs now, and we also got like massive pipes to Google.
Yeah, so it really depends on the actual problem that you're trying to solve then, and we cannot provide everything with a library, right? So we just provide, let's say, one building block, and then, the rest of the problem has to be looked at independently, I would say, yeah.
Okay. Thank you.
Thank you very much. Yeah.